what we have discussed so far is what is a system, and then what is a control volume. System made up of specific fluid particles, control volume, that is why I wrote stationary within bracket, fixed control volume within brackets when we define control volume. It could be moving as well, but in general they are fixed control volumes. What distinguishes control volume from a system is that the fluid particles which are in the control volume, they keep changing with time, that is a distinguishing feature. Now, having discussed system and then control volume, we are now going to move on to deriving the Reynolds transport theorem. We said we will do it in two steps, first for the simpler form and then the more general form. Now, what is the need for the Reynolds transport theorem? That is what we are going to discuss this slide. And okay. Now, the basic laws of physics, conservation of mass, momentum, energy are all stated for a system. Let us look at that. The mass of a system remains constant. That was very obvious as well. The way in which we define the system is that we are always focusing on 100 fluid particles. No fluid particle enters, no fluid particle leaves, which means that mass of the system is a constant. So, the conservation of mass is stated for a system. The mass of a system remains constant. Next, the Newton's law of motion. Let us state that the time rate of change of momentum of a system, I have emphasized that, is equal to sum of all the forces acting on the system. When we usually say, we say rate of change of momentum is equal to sum of all the forces. That is a very casual statement. If you want to very specifically say the rate of change of momentum of a system, you would imagine the systems whichever I come across, is equal to sum of all the forces acting on the system. The Newton's second law of motion is not for a control volume, the Newton's second law of motion is for a system only. Okay. Similarly, the first law of thermodynamics, here many of us should be familiar that the first law of thermodynamics is for a system, that goes without saying. Maybe for conservation of mass and motion we are not so familiar, but because first law of thermodynamics is discussed in the thermodynamics course. In fact, the first class of thermodynamics will start with the definition of what is a system, what is a surrounding. So, we are very familiar that the first law of thermodynamics is for a system. So, let us state that the time rate of increase of the total stored energy of the system, okay, is equal to the sum of the net time rate of energy addition by heat transfer into the system, okay, and net time rate of energy addition by work transfer into the system. The first law is known to you. What is to be focused is that we refer to the system. Okay. So, usually rate of increase refers to the time rate of change. Here it is made more specific here, time rate of increase of the total stored energy of the system, and that is equal to the rate of energy addition. That energy addition could be by heat transfer or it could be by work transfer. Okay. What is more important is total stored energy of the system and heat transfer into the system and work transfer into the system. The whole statement of first law is for a system. You would have called this as closed system, etc., but still the first law of thermodynamics is for a system. And we have the words net here because you can have outflow, inflow, etc. Energy can be added, removed, etc. That is why it says net here, similarly net here, etc. Okay. Now, the fundamental concept behind this slide, or what is that we should take away from this slide, is that all the basic laws of physics are for a system. Now, what is the need for the Reynolds transport theorem? If we go back to our first lecture, where we did experiments in this tank and then we used a mass balance equation to predict this flow rate, measuring these two flow rates, which means that we require a mass balance. That mass balance is required for a control volume, which means that all the conservation equations which we require are for a control volume. It could be the larger control volume or the smaller control volume, but still the conservation equations, already have used one of them. All the conservation equations are required for a entire control volume, but now the laws of physics are for a system. Okay. So, conservation equations or fluid flow are required for a control volume, as we have seen. Now, the laws of physics, as we have seen in the last slide, are all stated for a system. Okay. So, we need to relate the laws of physics as applicable to a system to the conservation equations applicable for a control volume. Let us emphasize that laws of physics as stated or as applicable to a system to the conservation equations applicable for a control volume. Whenever I say conservation equation, they are all for a control volume. So, I need to go from a system viewpoint to a control volume viewpoint. I should go from the laws of physics to the conservation equations, okay. And that is where we require a mathematical tool which relates the changes in a system to changes in a control volume, and that is what we call as the Reynolds transport theorem. Okay. So, this Reynolds transport theorem helps us to relate the changes in a system to changes in a control volume. Why is that? The changes in a system are described by the law of physics, changes in the control volume are what we require. So, that for example, we can use in such a case to predict flow rates, to predict velocity profiles, etc. Okay. Before deriving the Reynolds transport theorem, let us introduce some nomenclature. Now, in a thermodynamics course, you would have categorized properties as extensive properties and intrinsic properties. Okay. Let us do that here as well. We use capital B for extensive fluid property. What are the extensive fluid properties which are going to come across in this course? Total mass, total momentum, total energy, total species mass. Okay. Let us put them in terms of variables. Total mass is denoted by m, small m. Total momentum is mass into the velocity, okay. And then the total energy, in fact, if you want to say, I should say total energy. One total represents extensive property, another total represents sum of internal energy, kinetic energy and potential energy. So, this energy really means sum of all these three forms of energy. These values are per unit mass. This is internal energy per unit mass, kinetic energy per unit mass, potential energy per unit mass. You are multiplying by mass to get the total energy. And what is this? This is the mass multiplied by the mass fraction will give you the mass of the species. Okay. You would have done species balance equation in process calculation course. Okay. So, this is the mass of one component. For example, let us say a stream with sulfuric acid and water, this is mass of the sulfuric acid. Okay. Now, let us introduce intensive fluid property. Very simple, the extensive fluid property per unit mass is your intensive fluid property. Okay. Very simple, whatever variables I have explained there, just divide by m, you will get the intensive fluid property. Okay. For example, for the case of mass, you divide by mass itself, so it becomes unity. For the case of momentum, you divide by mass, you get velocity. So, now this velocity I can explain in two different ways. One is velocity, which is very well known to us. What is the other way of looking at it? Momentum per unit mass. When you divide this momentum per unit mass, by the mass, you will get the velocity. So, two different ways of looking at velocity. So, you should be able to view velocity in two different ways as we go along, and that is why I am explaining now, so that you get used to that. First is velocity as such, other way is momentum per unit mass, and of course, energy we divide by mass. As already explained to you, this all these represents energies per unit mass, internal, kinetic and then potential energy. That should be very familiar to you as well. And what is this? This is the mass fraction. You would have defined mass fraction as mass of species by total mass, exactly same meaning here as well. Okay. So, B can take on values 1 velocity vector, sum of all the energy terms, or mass fraction. So, B could take on any of these values. We have seen several examples of the intensive property B. Of course, how are they related? Capital B is equal to m into small b. The extensive property is equal to the mass into intensive property. Of course, the way in which we started is we define the introduce the extensive property. If you divide by m, you will get the intensive property. So, having introduced extensive property and then intensive property, let us move on to see how do we express rate of change of property for system and control volume. Why is that we do this? The objective of Reynolds transport theorem is to relate these two rate of changes. We want to relate the rate of change of property. When I say property, it could be mass, momentum, energy, species mass, etc. We use a general term property, but for easy understanding we will always relate it to mass, become easier to understand. So, rate of change of property for system, rate of change of property for control volume. How do we express that, and then how are they different for a simple case? That is what we are going to discuss in this slide. Now, we introduced the property B for a system. Let us express that in terms of variables which you would usually measure. For example, we measure density, and so we will express this B system in terms of the intensive property and the density. Let us see how do we do that. Let us take this example of the CO2 gas in the extinguisher. We said the gas inside the cylinder is taken as a system. What I will do now is split into small volumes, and which I call as capital delta V, delta capital V I. Throughout this course we are using small v for velocity, capital V for volume. Okay. That may differ from some fluid mechanics books, which we are following a small v for velocity, which I use several times. I think first time I am coming across volume, we are using capital V. So, what does delta V I mean? I split this system into smaller and smaller volumes. Now, the density can vary within the system. So, for each volume there can be associated density. So, this volume can have some density, this can have some density. So, within the system there can be spatial variation, and the density of each volume is rho I. Then each volume can have its own property value, intensive value, because this takes care of the mass. I multiply by the property by unit mass, so that I get the value of total property, amount of total property. So, what is B I? For example, let us say if it is energy, then energy for could be kinetic, potential, etc. for this volume, etc. and which I denote it as B I. If it is velocity, we have seen B could be 1, B could be velocity. So, then velocity in this volume, velocity in this volume. So, we allow for variation of the property within the system. We have split the system into smaller volumes and then multiply by the density of each of the volume, so that we get mass of each volume which we have split, and then multiply by the property per unit mass for that particular volume. So, that this whole term represents the amount of property for that small volume. Now, what do? We sum over all the volumes, I goes from 1 to the number of volumes. So, that this entire term represents the amount of property for the entire system. We split into smaller volumes and then multiply by density to get the mass of each volume, multiply by property per unit mass, get the property value for that small volume, summed over all the volumes, then that becomes the amount of property for the system. Now, what do? We make this volume smaller and smaller, which means that the number of such elements which we consider very large n tending to infinity, and so we take this sum in the limit of these small volumes become smaller and smaller, delta V, which is the volume of each element becoming smaller, we consider this limit. Now, in the limit of delta V tending to 0, this summation can be represented as this integral. Remember, there is assumption behind this representing summation as integral. What is assumption? Assumption of continuum hypothesis. Remember, when we discussed in the beginning, introduced continuum hypothesis, we said we can define differentiation, we can define integration only when we assume continuum hypothesis. I take here delta V tending to 0, which is valid only when the material completely occupies all the space. But then if it is not there, I cannot take this delta V tending to 0. So, it may look like writing the summation as an integral involves an assumption of continuum hypothesis. Okay. There it was introduced without a particular context. Now, there is a very good context to explain the use of continuum hypothesis or requirement of continuum hypothesis. Okay. So, this summation has become an integral sign. Remember, it is a volume integral over the, what is the volume we are considering? Volume of the system, and Bi has become B, rho has become rho. So, now we allow for continuous variation of rho and B within the volume. That is a distinction between this summation and this integral. Here it is a, we allow for discrete variation when you write as in summation. When you write for integral, you allow for continuous variation of those properties, namely density and B. Moment I say continuous variation, continuum hypothesis invoked. We use that to tell that it varies continuously. What is that we have done? B system has been represented in terms of the properties rho and then small b. As we have seen, B could be 1 for total mass, for momentum it is momentum per unit mass, which is velocity, and then these energies per unit mass are mass fraction. Okay. Now, what are we going to do? Express rate of change of B for system. That expression is as we write for any rate of change of any value in your calculus, d by dt of B. What is important is you should focus on the subscript, that is system. For example, it could be rate of change of mass for the system. We will take this as an example immediately. So, rate of change of property for the system, I replace this B system in terms of this integral expression. So, d by dt of this integral expression rho B dV, okay, integrate over the system volume. Now, let us write the rate of change of B for the control volume. Expression is not going to change. Whatever I have written here is applicable for control volume also, only the volume integral is going to change over the control volume defined by control surface. Okay. Now, so d by dt of B, the subscript now is control volume. What does this meaning of? We will see if when we take an example. So, d by dt of B for the control volume, I have replaced that in terms of integral expression. Why do I do in terms of integral expression? To allow for continuous variation within the volume. In this case, the subscript says control volume. So, this also volume integral, this also a volume integral, volume considered as the volume of the system, here the volume of the control volume, that is the difference. Okay. So, this is the rate of change of property of the system, and this is the rate of change of property for control volume. Of course, B is equal to m B. So, all these values, the intensive properties, if you multiply by m, you will get B. Okay. So, let us take an example of this fire extinguisher case, and let us take the example of mass. We will take B as the total mass as an example, in which case this small b becomes 1. What is that I have written? I have taken this expression and written for mass of the system. So, d by dt of mass of the system, right hand side I have d by dt, the b value is equal to 1. So, right hand side just becomes d by dt of integral of rho dV integrated over the system volume. Now, we have the way in which we defined system, the mass of the system is a constant. We have seen that as a law of physics also, because we are focusing on the same set of fluid particles, and so the rate of change of mass of the system is equal to 0. Because we are considering mass, the 0, if it were other variables, it need not be 0. Okay. So, in this particular case, because it is mass, the rate of change of the mass of the system is equal to 0. Okay. Okay. Now, what is the rate of change of total mass of the control volume? Now, d by dt of the mass of the control volume is equal to d by dt integral of rho b is equal to 1 and volume integral of rho dV, and the volume we are considering is the volume of the control volume. Now, what is this value? What is this value? Let us go back to this example. Our system at t equal to 0 is the gas which occupies the cylinder. At some time later, our system is composed of whatever gas which is escaped and whatever is remaining. That is why the rate of change of mass of the system is 0. Coming to the control volume, initially let us say I had some 10 kgs of CO2 inside the cylinder, sometime later some gas escaped and let us say it is escaping, and so this mass inside the cylinder inside a control volume will keep decreasing, and that is why this value is less than 0. So, while rate of change of mass of the system is equal to 0, rate of change of mass of the contents of control volume, we do not say rate of change of mass of control volume, that is not precisely correct. We say rate of change of mass in the control volume, or little more elaborately we say rate of change of mass of the contents of the control volume. For the system we can say rate of change of mass of the system. For control volume it is mass in the control volume or mass of contents of the control volume, very precise statements, and that value is less than 0. So, now as I told you, the objective of this slide was to express the rate of change of property for the system, rate of change of property for control volume. We also took a simple example to see that these two rates of changes are different. Rate of change for a system is different, even for the case of the simple example. For the case of taking mass an example, the rate of change of mass for the system is 0, rate of change of mass in the control volume is less than 0. Reynolds transport theorem relates these two rates of changes, that is objective of Reynolds transport theorem. How is the rate of change of property for the system is related to the rate of change of property for the control volume, and that is what is the objective of Reynolds transport theorem. Okay, let us move on. We are slowly learning concepts to start to derive the Reynolds transport theorem. First we discussed about system and control volume, then we introduced extensive variables, intensive variables. Now, in the previous slide we discussed about rate of change of property for system and control volume. Now, one more concept is required, what is called coincident system and control volume. The first step in the derivation of Reynolds transport theorem, we will say that we will consider a system and control volume which are coincident with each other. What do I mean by that? Okay. Symbolically, in terms of expression, this is how we write the property of the system, in this case capital B, is equal to property of B in the control volume at a particular time t. Okay. We quickly say as B system is equal to B control volume. In terms of statements, B of the system is equal to B in the control volume at time t. Now, we will take our well known example, flow between these two parallel plates. Now, I have two demonstrations here, the same demonstration at different stages. As the fluid flows through between these two parallel plates, let me explain what I have drawn here. This is the top plate, the bottom plate, this is the axis, and then this is the control surface through which there is inflow, this is a control surface through which there is outflow. Okay. This nomenclature is required to understand what I am going to show now. So, the top plate, the bottom plate, and then the control surface with inflow with outflow. So, which means these 4 lines, this and this defines the configuration, the control volume, and of course, there is a control surface here, and here also there is a control surface, though I have not shown that, only the plate is shown, and this is the axis. Now, we want to define our system. Now, I have different choices for defining my system, and what is shown here are different choices for a system. Okay, let me stop. For example, I can color a portion of the fluid as it is shown here and call that as my system. Okay. Let me just go ahead. I can do this as well. I can color this portion of the fluid and call that as my system. Now, let us proceed. These are several options for the system. So, these are several options for the system. Now, what is the most convenient way of defining my system? Several options are there, which is more convenient. Remember, system was little more imaginary. So, it will be convenient for us if we define a system whose boundaries are well defined. In the example of the fire extinguisher, so initially we had the system as whatever was occupied by the whatever was occupying the tank. Sometime later some system escaped, etc. So, now system boundary can be anything, but we need to define a system which is more convenient to us and whose boundaries are well defined. So, now you just watch the different options of system. The best option is when the system coincides with the control volume. Why do we do that? The boundaries of system are also well defined and coincides with that of the control volume, for which we need to derive the conservation equation. So, that connects the boundaries for the system and the boundaries for the control volume, they just coincide, so that we can relate the laws of physics to the conservation equations. Okay. You will see a message saying coincident system and control volume when that system exactly coincides with the control volume. Okay. I will show that in the next video as well, but try to catch that moment. Yeah, coincident system and control volume, of course, it just came like a okay. Now, I can choose these also as control volume. For example, whatever shown here, I can choose this also as my system, and then I can choose this as my system. So, I can choose system which is just entering, which is just coincident, or leaving, which is most convenient or which is most well defined is the system which is coincident with the control volume at any instant of time. At every time whatever system is coinciding with the control volume, that is defined as my system. Okay. This is what I have shown in the next video, where I just stopped the animation at the point where system coincides with control volume, in case you are not able to see in the earlier case. Yeah, caught right at the moment, the coincident system and control volume. Several possibilities for selecting system are there, but the most convenient, most well defined possibility is the system which is coinciding with the control volume. Remember, it is at every instant of time, every instant of time.